Okay, hello everyone. In a new video, so we have reached part 12 of chapter 5, which is the chapter of kinematics for grade 11 students. So now in this one we are going to solve some exercises. Before we do so, let me mention the following notes. So let me start by note number 1. Okay, suppose here we have a circle. So this is the x-axis, this is the y-axis, and here we have a circle. And a particle m is rotating on this circle in the anti-clockwise direction. This is the positive x-axis and this is the positive y-axis. This is the origin O and this is the position vector OM. Which is the position vector R. So suppose that we are interested in determining the number of revolutions done while m is moving, either in the positive direction or the negative direction. So knowing that each 2 pi, so always angles in the SI are expressed in radians, not in degrees, corresponds to 1 revolution. And by revolution I mean the completion of one turn, one complete turn. So this corresponds to an angle of value 2 pi expressed in radians. So in this case, what about an angular displacement delta theta? So delta theta here is said to be the angular displacement. So all of these quantities have the same name in the case of rectilinear motion, but they are preceded by the word angular. So angular displacement corresponds to what? So this is equal to n. Now if we cross multiply, then in this case n is equal to delta theta multiplied by 1 divided by 2 pi, which is equal to delta theta divided by 2 pi. So n, which is equal to delta theta divided by 2 pi, corresponds for the number of revolutions corresponding for an angular displacement delta theta. Now as for note number 2, we know that in the case of the angular quantities, we have theta, omega, alpha. So this is the angular position, angular speed, angular acceleration. As for the Cartesian, we have say for example x, y, so this is the position, we have v, we have a. This is said to be the linear speed and this is said to be the linear acceleration or the Cartesian acceleration, okay, and the Cartesian speed. So sorry, linear acceleration. These the naming of quantities doesn't change the physical interpretation, okay, we just name them for our convenience, okay. So in order to distinguish just between angular and linear and the linear quantities. Now moreover in number 3, let me say the following, that we know that a is equal to axi plus ayj. In this case the acceleration, the magnitude is given by the square root of ax squared plus ay squared. This is in the Cartesian basis. Now moving to the Frenet basis, we know that a can be expressed, so both of these are the same, they are the linear acceleration or the total acceleration. it's equal to a n I, so the normal acceleration plus the tangential acceleration, j, and in this case a is also equal to a n square plus a t square. Okay, but notice that, note, a n is different than ax, is different than ay, is different than a tangential. In some cases it happens that they are equal, but this is not a general rule. So in general, these components are different than each other. Okay, so the Cartesian decomposition is different than that of the Frenet decomposition. Okay, so what else? So these are the notes that I wanted to discuss before we start solving some exercises. Okay, so let's start by exercise number 27. So they are telling me the angular abscissa of a moving particle as describing a circular trajectory of radius r is defined by theta is equal to minus t squared plus 42 radians, and radians corresponding to the unit of the angle, which means that we are in the case of the SI unit. So here we are simply discussing circular motion, so it's convenient on the scratch to write the equations of circular motion. The uniform circular motion is given by theta is equal to omega t plus theta 0, omega is equal to a constant, alpha is equal to 0. As for UVCM, we have theta is equal to half alpha t square plus omega 0 t plus theta 0, omega is equal to alpha t plus omega 0, and alpha is equal to a constant. Now referring back to the exercise, they are telling me indicate the nature with the justification the nature of motion of S. So we know that the trajectory is already given by circular. So since theta is equal to minus t square plus 40t, notice that the angle is quadratic in time. Whenever the angle is quadratic in time, or the angular position, so why do we name theta to be the angular position? Because in the rectilinear motion this is given by position, so this is simply the angular position. So everything is preceded by angular. Whenever it's quadratic in time, it means that UVCM verifies the general form theta is equal to half alpha t square plus omega 0 t plus theta 0. Then the type of motion is UVCM. Now in number 2 they are telling me determine the angular velocity of S at any time t. Recall that in case of the rectilinear motion, the speed the velocity is determined by referring to the type of motion. So here let's say since the type of motion is UVCM, then we can use the following equations. So theta is equal to half alpha t square plus omega 0 t plus theta 0, omega is equal to alpha t plus omega 0. Moreover, alpha is equal to a constant. Given that theta is equal to minus t square plus 40t, we are interested in determining the angular velocity, which is corresponding for omega. In order to do so, we need to specify alpha and omega 0. So by comparison, we get that half alpha is equal to minus 1, comparing the quadratic terms, which means that alpha is equal to minus 2 radians per second square. Now as for omega 0, comparing linear terms, you have that omega 0 is equal to 40 radians per second. Then in this case we can say that omega is equal to minus 2t plus 40. So notice that in this case the moving particle, okay, so it's undergoing UVCM motion. So number 3, they are telling me determine the time taken by S to stop. So we need to find time, the instant time t or the duration, by S to stop. And S stop is given by the equation omega is equal to 0. So we have that omega is equal to minus 2t plus 4t. Knowing that we are interested in determining time, knowing that it will stop, so omega is equal to 0. So what's the type of this equation? Linear equation, and one unknown, the unknown is t. So in this case t is equal to 40 divided by 2, which is equal to 20 seconds. So t is equal to 20 seconds. So let me do this part 4 here, because I will need the above equations. Now in part 4 they are telling me calculate the number of revolutions accomplished by us. We know that the number of revolutions is given by delta theta divided by 2 pi, in which the value of pi is given by 3.14. However, delta theta, which is the angular displacement, is equal to theta final minus theta initial, which is 0. So in this case, theta 0, comparing this with this, so theta 0 is 0. Now what about theta final? Theta final corresponds to the instant where m stops rotating. So theta final is equal to theta computed at t is equal to 20 seconds, because this instant corresponds for the instant where theta stop moving. So this is equal to minus 20 to the power 2 plus 40 multiplied by 20. Now plugging this on the calculator, then we have that minus, so this is equal to 400. Since everything is expressed in the SI, so the value of theta f will be in the SI, which is radians. So now in this case the number of revolutions is given by 400 divided by 2 pi revolutions, okay? And you can calculate the decimal form of this, which is given by 2 shift pi. So it's almost given by 63.66 revolutions. So I didn't complete the revolution, so it's given by 63 revolutions, okay? So this is it for exercise number 27. Now for exercise number 28, they are telling me in a circular motion of r is equal to 0.1 meters, or small r, let me say. The angular abscissa theta of a moving particle m is in the form, okay? So here it's obvious that the trajectory is circular, so let's write on the scratch the equations of motions related to UCM and UVCM. So as for UCM, they are given by theta is equal to omega t plus theta 0, omega is equal to a constant, alpha is equal to 0. As for UVCM, theta is equal to half alpha t square plus omega 0 t plus theta 0, and omega is equal to alpha t plus omega 0, and alpha is equal to a constant. They are telling me determine the angular and the linear velocities. In order to determine the angular, so first let's determine the angular. In order to determine the angular velocity, first we need to study the type of motion. So let's say since theta is equal to tan t plus tan verifies the general form. So notice that here the angular position is linear in time. Whenever it's linear in time, then the type of motion is UCM. Then So in this case, theta is equal to omega t plus theta 0, omega is equal to a constant in which alpha is equal to 0, and the given form is given by theta is equal to tan t plus tan. So by comparison, we can say that omega is equal to 10 radians per second because everything is expressed in SI. Now here they are asking me about the linear velocity. We know that omega and v are related via the following formula. V is equal to r omega. Now the value of r is given by 0.1 and the value of omega is given by 10, so this is 1 meters per second. So v is equal to 1 meter per second. And here we know that velocity is a vector quantity and this is the speed. But whenever we are talking in circular motion, so here in the question they must be more specific and to mention the magnitude of the linear velocity, okay? So let me say the following here as a note. Note number 4. We will only consider scalar quantities in circular motion unless specified, okay? So we can consider only the scalar quantities unless they tell us calculate or they mention the word vector, okay? Now in number 2, so let me say that omega is equal to 10 radians per second and v is equal to 1 meters per second. Now in number 2 they are telling me to determine the angular acceleration. So in this case the angular acceleration is 0 and then deduce the tangential one. We know that the angular acceleration and the tangential acceleration are related via the following formula. At is equal to r alpha, so it's r multiplied by 0 which is equal to 0, so At is equal to 0. Now in number 3, calculate the acceleration of m. So I repeat here, we are only interested in the magnitude. We know that the acceleration is either given by square root of ax square plus ay square or the square root of an square plus at square. Since we are talking about circular motion, it's more convenient to discuss Frene basis. Then it's given by the square root of an square plus at square. So the value of at is 0. Now it's left to determine an. An is given by v square over r. The value of v we have calculated, which is given by 1 independent of time, so 1 to the power 2, divided by the value of r, which is given by 0.1. So this is equal to 10 meters per second square. So this is equal to square root of an square. They cancel out, which is equal to an. So this is equal to 10 meters per second square. So the magnitude of the acceleration is given by 10 meters per second square. Now finally in part 4 they are telling me to determine the frequency and the period of this motion. We know that omega and f are related via the following formula, that omega is equal to 2 pi f. So if you are interested in f, then f is equal to omega divided by 2 pi. The value of omega is given 10. So the frequency is given by 10 divided by 2 pi and the unit is hertz. As for the period is given by 1 divided by f, so 1 divided by 10 over 2 pi, which is equal to 2 pi divided by 10, and in seconds, so the period is given by 2 pi. Okay. Now as for exercise number 29, They are telling me a puck M moves along a circle trajectory C of radius R is equal to 4 centimeters. So knowing that centimeter is not the assign unit of length, in order to convert from centimeters to meters, we divide by 100. Then 4 divided by 100, this is equal to 0.04 meters. The angular abscissa is given by this. So here we are studying circular motion, so it's convenient to write on the scratch the equations of circular motion that are given by. So in the case of UCM, they are given by theta is equal to omega t plus theta 0, omega is equal to a constant, and alpha is equal to 0. In the case of UVCM, they are given by theta is equal to half alpha t plus omega 0 t plus theta 0. Omega is equal to alpha t plus omega 0, and alpha is equal to a constant. Now in number 1, they are telling me determine the expression of the angular speed of m. So in order to do so, we need to refer and to study the type of motion, and this is done by comparing the given form to the general form. So since theta is equal to 4t square plus 2t plus pi verifies the general form, theta is equal to half omega t square plus alpha plus omega 0 t plus theta 0, then the type of motion is UVCM whenever it is quadratic in time, which means that it is what? UVCM. So in this case, theta is equal to half alpha t square plus omega 0 t plus theta 0. Omega is equal to alpha t plus omega 0, and alpha is equal to a constant. And the given form is given by theta is equal to 4t square plus 2t plus pi. So by comparison, if you are interested in determining the expression of the angular speed, which is omega, we need to find alpha and omega 0. So comparing quadratic terms, we find that half alpha is equal to 4, which means alpha is equal to 8 radians per second square. Now comparing linear terms, we see that omega 0 is equal to 2 radians per second. And in this case, the general expression of the angular speed as function of time is given by omega is equal to 8t plus 2. Then deduce the expression of the linear one, and by deduce it means that we need to use the previous part. In the previous part, we have determined omega and we are interested in determining v. We know that omega and v are related via the following formula: v is equal to omega multiplied by r. So it's given by 8t plus 2 multiplied by the value of r, which is given by 0.04 in the SI. Now let's expand here. 8 multiplied by 0.04 is given by 0.32 multiplied by t, plus 2 multiplied by 0.04 is given by 0.08. So in this case, the speed, which is the magnitude of the velocity, which is the linear velocity, is given by v is equal to 0.032t plus 0.08. Okay. Now in number 2, they are telling me to determine the angular acceleration of m. So this is already done. So the angular acceleration alpha is given by 8 radians per second squared. Okay. Now in number 3, they are telling me find the magnitude of the tangential acceleration vector. So we know that the tangential acceleration, the magnitude and alpha are related via the following formula: alpha r, the value of alpha is given by 8 and the value of r is given by 0.04. Then this is given by 0.0, sorry, Here it's 32. So radians per second square. Okay. Now in number 4, sorry, this is not radians per second square, this is meter per second square. Let me check. None of this. Okay, so here make sure that it is meter, and we didn't discuss here. Okay. So now they are telling in part 4, determine the magnitude of the acceleration. The acceleration is given by either the square root of ax square plus ay square, or the square root of an square plus a t square. Whenever we are talking about circular motion, it's more convenient to discuss the Frenet basis, so it's given by the square root of an square plus at square. Now we have the value of at, which is given by 0.32, which is constant independent of time. Now in order, so this is equal to square root of an square plus 0.32 to the power 2. In order to determine the value of a, we need to determine the value of an. Notice that an is given by v square over r, in which the value of v depends on time. So v is equal to 0.32 t plus 0.08. We are interested in determining v at the instant t is equal to 2 seconds. So 0.32 multiplied by 2 plus 0.08, which is equal to 0.72 meters per second. Now an is equal to 0.72 to the power 2 divided by the value of r, which is 0.04. So this is equal to 12. Sorry, something wrong. Okay, just 1 second. Okay, great. So everything is correct, I expect. So this is given by 12.96 meters per second square. Now the value of a is given by, sorry, here, square root of 12.96 to the power 2 plus 0.32 to the power 2. Okay, let me do it again. So this is equal to 12.96 meters per second square. So the acceleration is given by 12.96 meters per second square, and as you can notice that the majority of the acceleration is not due to the change of the speed, because this is very small. However, it's due to the change in direction. Now in part 5 they are telling me determine the number of revolutions which is given by n is equal to delta theta divided by pi, accomplished during the first 4 seconds of motion, knowing that m starts moving at t0 is equal to 0. So delta theta represents the angular displacement between the two instants theta 1 and theta 0. Theta 1 corresponds for theta computed at t is equal to 4 seconds, which is the final instant, because 4 seconds is greater than 0. So 4 multiplied by 4 to the power 2 plus 2 multiplied by 4 plus pi, this is equal to 75.14 radians. As for theta 0 is equal to 4, so it is theta computed at the instant is equal to 0, which is equal to 4 multiplied by 0 to the power 2 plus 2 multiplied 0 plus pi, which is equal to pi, which is equal to 3.14 radians. Now delta theta is equal to theta 1 minus theta 0, which is equal to 75.14 minus 3.14, which is equal to 72 radians. Now n is equal to 72 divided by 2 pi, so this is the number of revolutions. Now if we give the decimal form of this number, so this is almost equal to 11.45 revolutions, which is 11 revolutions. Okay, so it doesn't reach a 12, it doesn't complete a 12th revolution. So this is it for exercise number 29, and let's solve the final exercise, which is exercise. Okay, let's leave this exercise for another video. Okay, so that's it for me in this video, guys. In part 13 we'll complete solving exercises on this chapter.